Okay everybody, so here's just a quick follow-up video on this signal tracer. As I said, I'm getting ready to do that Hallicrafters repair and restoration and whatever. But I just want to show you a little mod that I made, and it is that bias mod we were talking about. It turned out to be a lot easier than I thought it would be. I did a lot of testing, and after all the testing that I did, this is what I came up with, and I'll demonstrate right now to you how it works. So right now I have a signal of about 1 megahertz. Let's turn on some modulation, and 200 millivolts of signal. So it's a pretty strong signal. So that would be kind of down the lane a little bit on your IF stage. And if we look down here, turn it on, you can hear it's distorting. There's so much signal in there. You hear that? So there you go. And I'll keep moving the microphone back and forth so you can hear it. So now let's I'm going to leave this on here so you can listen to it. And I'm going to go back to the camera. And we're just going to drop the millivolt level down, or the signal level down, amplitude, until we can't hear a signal anymore. So let's well, that didn't take long. Now if I turn this up, you can just barely hear it. So at 63 millivolts, we're pretty much getting all we can get. And by the way, that is actually 63 millivolts. If you look back up here again, you can see that I have this 50 ohm terminator on here. It's like an inline load. So these need to be, the signal needs to be fed into a 50 ohm load. And since it's a real high impedance input, that's why I have this. So what's here is very close to what's actually going into the signal tracer. So that's pretty much all we're going to get out of this thing. Now watch what happens when I turn on the bias. Big difference, huh? All right, let's go down and see how far down we can go now. Sorry, it was picking up my microphone. Take a look at this. Yeah, that's the transmitting of the wireless mic. Okay, so if I turn this off, on, so let's keep going down now. So that's about all we can hear right now is 6.3 millivolts. See that? 6.3 millivolts. So that really improves it. So we went from, what was it, 200 millivolts, a little bit below that, clear down to about 6. So you can see how much that bias fixes it, or how much more sensitive the bias makes it. So let's just do a quick refresher on how an envelope detector works with a diode. And what we're going to do is we're just going to ignore all this in the front end, because really this has to do with loading of the signal that's coming in. But essentially what's going to happen is you have your RF carrier coming in here. It gets through this capacitor, because the capacitor will pass the high frequency and it will block low frequency. So this is actually a high pass filter is what this is. So any DC component is not going to pass through here. So what's going to happen is, we know that the forward voltage drop of one of these diodes is going to be in the hundreds of millivolts, right? Even a Schottky diode has around a 300 millivolt forward bias, meaning that if the voltage doesn't get above that 300 millivolt threshold, the diode will not conduct in forward direction. So you might say, well, how is it that this thing can pick up a lower signal than 300 millivolts? Well, here's the really cool part how this works. Essentially, what's happening is, if you look at the peak value versus the RMS value of that signal that's coming in there, let's say it's a 200, it's in the microvolts or so. What's going to happen is those little peaks are going to make it through this diode. This diode actually isn't like a switch. In other words, it isn't like at exactly 300 millivolts it starts to conduct, and at 299 millivolts it doesn't. Basically what's going to happen is, at very low signal levels, and it's much lower than 300 millivolts, this diode will somewhat conduct. Just the little peaks will make it through there. Tiny amounts of current will flow. And that tiny amount of current will actually go through this C4 and begin to charge it up. It's only going to allow the current to flow in one direction. So in all intents and purposes, this is DC voltage. And what it's going to do is, it's going to create a time constant with this line right here, and it's going to charge this little capacitor up. Each little pulse charges the cap a little bit more. Now, as I said, it's extremely tiny current, but remember, even at AM, intermediate frequency, that's 455 kilohertz. So 455,000 pulses every second put a teeny little bit of current into this capacitor and charge it up. Eventually, this cap will charge up to a certain point to where there's actually a differential between here and here, where you have your 300 millivolt drop. So it allows this to forward bias. So it's kind of like putting a DC bias on it. Now the only problem with that is, and then you have this 100K that helps bleed that off. So it's essentially what you're going to have is something like this. This is an equivalent circuit of what you got. So the pulses come in through here, they get rectified. That tiny little bit will get in here and it will charge this capacitor. Basically that 2.2K and that, up here, the 2.2K and the 20K are in series. So that's a 22.2K. So you have a voltage divider here and this diode in the middle. And the capacitor is going to charge through all of this like a time constant. And then this is going to actually discharge the capacitor over time. So this affects all of this as well. And that's what sets up that little bias voltage. Now, this isn't ideal. It will allow this diode to pass a much smaller signal than if you were just trying to pass DC current through there. But because of the charging of this cap. But it's not going to work as good as if we put an actual bias voltage on there. By adding that DC voltage at this point here, it actually puts constant current through here and keeps this capacitor charged ahead of this. And this loading here also has to do with how much of the signal gets to the output. So you really can't mess with this too much. This whole thing is kind of balanced to work this way just because of the characteristics of the diode itself. And yes, this is a Schottky diode, so I should put the little thingies on there. But anyway, like that. I know I'll get yelled at if I don't put the right symbol. So anyway, that's how this works. It's pretty cool. So yes, this diode in its current form can actually conduct at much lower than its actual forward voltage drop voltage, which would be the bias voltage would be, like I said, 200 or 300 millivolts. But we can have signals in the you know, several hundred microvolts, or well, several millivolts anyway, can get through here. So let's move on and look at how the rest of it works now. So what we're doing, as you can see, there's only 3 components I added. That's here, here, and here. There's a 0.1 microfarad capacitor. Now that just acts like a filter, a low-pass filter. And what's going to happen is any of the high frequency that's coming in off this RFN and leaks through this 1 meg resistor, which is going to be really tiny by then, it's going to get shunted to ground before it can go into our battery pack. That's all that does. Is it super necessary? Probably not, but it's there. There's a 1 mega ohm resistor and a switch to turn it on and off, and that's it. All the rest of this is just bone stock circuit. So by adding this 1 meg resistor from your DC power source, so you have your 9 volts through this into there, what this is going to do is it's going to form a voltage divider. And I'll kind of draw it out here with this old pencil. Look at this more like something like this. You have 9 volts, you have your 1 meg, you have a 22K, and then on this line you have the Schottky diode, and then this 100K resistor. So this is 22K, 100K, and then the junk underneath here, and then the diode, and then this goes to ground. So essentially it's kind of a voltage divider, and there's your 9 volts. So really what's happening is this is coming through here, and it's just splitting off between these two here. So essentially all this is going to do is divide between this network and this diode here, and it's going to give us approximately that 0.2, 0.3 volts you need to turn this diode on. So basically the diode is already in forward bias. Now how do we get away with that without it getting into our signal? Well, if you look at the input here, here's a DC blocking capacitor, and that prevents DC from getting on the incoming signal here. And then at the output, where it goes down into the potentiometer, which goes into the amplifier, there's another blocking resistor. So all the DC component is contained in this diode area. So this was set up for this modification. It just made it perfect. And it just so happened, I tried all kinds of things. I tried putting a pot here with voltage dividers, and I tried adjusting this, and none of it really made that much a difference from just putting the 1 meg resistor with the battery on there. Tiny little bit of difference. You could adjust this 100K to fine tune that voltage drop across this diode, but really it's so close. I looked at it on the scope. It's almost spot on where it needs to be. It just worked out that way, I guess. So the secret sauce is the fact that it's a 1N5711, and the values of these 2 resistors, and that this is a 1 mega ohm resistor. It makes it very close to what you need. So what's that do? Well, if this diode is in forward bias, then any tiny little signal that comes through here is going to pass right through there. It's going to ride on that DC carrier and then pass through here. And that's why when it was turned off, you couldn't hear the low signal until it was able to forward bias this diode. But when you put this on here, then it could. It's a very simple circuit. Now what happens if you have an even tinier signal? You don't always have to look at something that tiny, but what if you do? So you can see we're getting nothing here. We turn this on. You can just barely hear it. and that's 6 millivolts. If I go down to 5 millivolts, it's probably not going to hear it. Very quiet, but it's there with the volume turned all the way up. Okay, so now let's get crazy. Okay, so what I've done is I've added this little amplifier here. This is a wideband low noise amplifier, and let me get my microphone where you can hear me. It's got a 34 dB gain, so basically what it's going to do is it's going to take the voltage level that's going at the input and it's going to amplify it by a factor of 50. So if I have 1 millivolt going in, I will get 50 millivolts coming out. So that's quite a bit of gain. It just runs on 12 volts, and that's what this is, the 12 volt supply. Most of them run on 5 volts, and I have a bunch of those little, these can be purchased very inexpensively, especially the little circuit board ones. You can get them for $10 online, literally. They even make ones for a little more, 30, 40 bucks, something like that, 50 bucks maybe, that have a built-in battery pack that's USB chargeable, so you don't even need a power supply. So anyway, all I'm doing is the signal generator is now just going straight into here. This is a DC blocker, and anytime you're going to use something like this on a live circuit, you would want this here to block any DC component from damaging the input of the amplifier. And then I'm coming out of here and going up into the signal tracer. So let's hear what happens now. I'm still at 5 millivolts. Let me turn this on. Okay, I'm really swamping it out now. You hear that? I'm at 5 millivolts. So now let's go down a little bit more on the amplitude. Okay. So now, instead of hearing 5 millivolts, I'm hearing 1 millivolt. And now let's turn the bias on. And let's go down some more. So there, I can barely hear it. I don't know if you could hear that. Hold on. Now let's see where we are. Check it out. 200 microvolts. Now we're down into the weeds pretty much. And again, now you're going to need something like a spectrum analyzer or something to see a signal that tiny. But yes, even with that little amplifier module, you can, and that bias, you can get signals as low as 200 microvolts now and measure them and be able to hear them. Now a gain of 50 is good for what we're doing here, but you can actually daisy chain these and you could put another one in line with this, or you can buy one of these with higher gain yet. And if you do that, then you can use these little things. And these are called near field probes. And what these do is these will detect an electromagnetic field in close proximity to the coil. These are little PC boards. You can buy these on eBay, AliExpress, Amazon, whatever. If you get these cheap PC board types, a whole set of them is like 12, 15 bucks. They also make really high-end ones that you can spend $500 on, and they're a lot more accurate. But each one of these works within a frequency range. So if you're just working with stuff in broadcast radio range, like shortwave, FM, AM, whatever, you just need one probe. I mean, just the one in that range. But these will even go up into the gigahertz. And what you can do with those is you put that extra stage of amplification in there, and now this thing becomes a near field wireless probe. So there's lots of things you can do with this little kit if you want to get creative. And I just wanted to show these couple of mods to you, and maybe we will be using them in the future. So that's it for now. Now you see how this all works. And until next time, I wish you peace, joy, happiness, and good health in your lives. And stay tuned very soon for the video on the Halocrafters.